Yes, yes. Yeah. So we welcome back Dan to our seminar, and he will be talking about applications of Rees valuations in today's seminar. So at the end, we can have discussion. During the seminar, please type your questions in chat box, and we will transmit them to Dan. Unfortunately, we cannot see him today because of some camera problems, but the document camera is working fine. And please save your questions until the end. So Dan, you are welcome to begin your seminar.
Okay. If someone has a question, they can just turn on their mic, because when I have the image of the document cam, I can't see the Google Meet setting. So I'm going to start where I left off last time, talking about the connection between the Rees valuations of an ideal and the Rees valuations associated to the completion. And so the setting is R is Noetherian. The height of the ideal I is greater than 0. And P is a prime ideal containing I. And now I'm going to slightly different notation, but just to indicate that it's not the local case. So these will be the Rees valuations, or Rees valuation rings, centered on P and V tilde P R hat, sorry, R P hat, I R P hat. These are the Rees valuation rings. Let me see. Is that image too bleached out?
We can read what you are writing. Yeah.
Okay. All right. Those are the Rees valuation rings of I centered on the maximal ideal of the completion of R localized at P. And of course, the first one here is also the same as the Rees valuation centered on P after you've localized. And that's really the crucial case. The difference here is we're not assuming that these are what we call M valuations. Valuations centered on the maximal ideal of a local ring whose residual transcendence degree over the residue field is one less than the degree of the ambient ring. And so what happens here is you assume by localizing at P, but this is just the global statement, you can assume this is local. And then what you have to do is you look at this following sequence of integers. And these are the dimensions of R hat mod Z, where Z is again contained in the completion of R. It's a minimal prime. Such that the analytic spread of I R hat mod Z is dim. R hat mod Z. So before, the V sub M had to have analytic spread when you went to the completion and modded out the minimal prime. We were looking at those primes for which you had true maximal analytic spread equal to the dimension. And so those gave rise to the so-called M valuations among the Rees valuations. Here, we're just considering all Rees valuations centered on the prime P. And so what happens is you have to look at the primes in the completion that are, off in the distance, the minimal primes for which the ideal has maximal analytic spread, but not necessarily equal to D, the dimension of the ambient ring. Okay, so you can call these primes Zij. These are the minimal primes in the completion. There may be more than one, right, for each possible D. Oops, let me see. This was R. I just want to keep my notation, HI. Okay, so what that means is there are HI minimal primes of dimension DI. Okay. Now, from what we talked about last time, if you look at the prime centered on the maximal ideal of the completion, these, all the Rees valuations come from modding out minimal primes. So you have a bunch of, the point is for each minimal prime Zij, there's some Rees valuations. Oops, this should be of I here. For each ij, right, that's a minimal prime, and then there's some Rees valuations, and Cij just, I guess this would be, keeps track of them. And then, of course, for every one of these, oh, sorry, I didn't state the conclusion. Then there's a one-to-one correspondence. Between these two sets, V tilde P I and V tilde P are localized at P completion I. In any case, what I'm trying to say here is that this is all now determined by the primes, minimal primes in the completion, such that when you extend the ideal, it has maximal analytic spread relative to dim R hat mod Z, whereas before it had to always have just dimension D. And then, B tilde of MI will just be the intersections. These are the Vij, Cij, which are Wij, Cij, intersect K, Zij, intersect R. So mod out the minimal prime in the completion and contract your DVR back. And then the point is that, things are still determined by maximal analytic spread, but relative to the dimension that you got. And by definition, any Rees valuation, right, comes from first modding out a minimal prime and looking at some DVR and the corresponding residue field. So this is how the correspondence looks in the general case. So again, just to remind you, last time we were mainly focused on Rees valuations that were M valuations centered on P. These are just all the Rees valuations centered on P. And so you have to look at different heights among minimal primes, dimensions among minimal primes, but only taking those that have maximal analytic spread. And then you can draw a similar diagram to the one that I had last time, so that all these minimal primes are parameterized, the different Rees rings. So these are minimal primes in the completion. I won't draw the whole diagram. Then you have your WI11, WI1, TI1, VI1. T, I1. And then you have something similar here. But you now have families of minimal primes that you're looking at. With I fixed, it's the dimension is di, and the analytic spread extended to that factor ring. The completion modulo of the minimal prime is maximal, but it's just whatever that dimension is. So you can keep track and have a correspondence between all the minimal primes centered on a given, all the Rees valuations centered on a given prime in a fashion like that. Okay, there are further connections between Rees valuations and completions. An obvious thing from what we've said here is that, of course, well, I guess you need locally quasi and mixed, then the number of Rees valuations here you're in the local case is bigger than or equal to the number of minimal primes. In the completion. And of course, Rees's strong valuation theorem tells you something about the completion. R is using Rees valuations analytically and ramified again. We referred to this before, but now we can use Rees valuations if and only if there exists an M primary ideal. Such and T of I greater than 0. By the way, if I start running off the page, let me know, because the camera doesn't show the whole page. Such that the min over I, Vi of x is less than or equal to Vi x plus Ti for all x. And this min is over the Rees valuations. So it's just another way of saying Rees's theorem, but using Rees valuations. And then there was a nice result, similar vein of Judy Sally, if R is analytically unramified.
So if you can shift the paper a little up.
Yep, thanks.
Thank you.
You have an M primary ideal. And if the number of Rees valuations, necessarily, if there's one Rees valuation, it has to be an M valuation. If there's just one, and she called this one fibered. The ideal is one fibered. That implies R is in fact analytically irreducible. In other words, its completion is an integral domain. And there's a nice argument an expository account by Irene Swanson. So it works. So suppose the k is chosen so that I to the n plus k, the integral closure is contained in I to the n for all n. That's a consequence of being analytically unramified. And then suppose V is, let's see, I guess you write it this way. The set consisting of V is your only Rees valuation. and that when you extend I to V, it's just the rth power of the maximal ideal of the Rees valuation. Then if you look at the maximal ideal in R raised to the n plus kth power, that's certainly contained in the same power of the maximal ideal of the valuation ring. Okay, but that's I to the n plus k V intersect R. But remember, when you extend to all the Rees valuations and contract back, you get the integral closure, which is then contained in I to the n, which is contained in m to the n. So now you notice that the powers of m and the powers of the contraction of the maximal ideal from the valuation are cofinal. So R is a subspace when you think topologically. So when you take the completion, R hat is contained in V hat. But of course, this is a DVR and hence an integral domain. So this is an integral domain. So if there's one Rees valuation associated to an M primary ideal, then you're going to have an analytically irreducible local ring. Of course, it's not an equivalence, as the work of Katkowski shows. And so you don't get a characterization of analytically unramified using valuations. However, as many people know, there's Azumi Rhys, which does exactly that. So Shunzo Azumi originally in the geometric or analytic setting showed that you could use M valuations to characterize analytically unramified local domains. And then Rhys extended that to the purely algebraic setting. So the original statement of Rhys looks like this: Rm, a local domain, then R is analytically irreducible. You can say it a couple of different ways. I'll say it this way: if and only if there exists an M primary ideal, I, and constants, C prime bigger than 0, such that what? Such that V I of x y minus V I of y is less than or equal to C V I of x plus C prime for all non-zero x and y. Okay, and to prove this, he proved something else that gives you information about Rees valuations. So what he proved is the following. To use, for one direction, he used and proved the following, which I think gives a good, which can be applied to Rees valuation. So if you have Rm, a complete local domain, and VW, M valuations. So those are the actual valuations as opposed to the valuation rings associated to Rees's notion of an M valuation, which you recall are divisorial valuations. Then there exists a C greater than 0, such that v of x is less than or equal to c times w of x for all x not equal to 0. Now, in a complete local domain, valuations, if you have an M primary ideal, all the Rees valuations are centered on the maximal ideal. And because of a complete local domain is universally catenary, or which is equivalent to being locally, finite extensions of it are locally quasi-unmixed, then those Rees valuations will automatically be M valuations. So in particular, this statement could apply to any two Rees valuations. Okay, and then that latter statement was improved by Hubel and Swanson. Namely, if R is analytically irreducible, given an M valuation V. Oh, by the way, the converse is also true in the sense that M valuations are Rees valuations of an M primary ideal. But if you're given two arbitrary ones, they might not be M valuations of the same M primary ideal. So they strengthened Rees's statement in the following way. So given an M valuation V, okay, there exists a C greater than 0, such that for all M valuations W, you have V of x is less than or equal to C times W of x. So one C works for all W. Once you've established V. Okay, so those are nice things that relate to the completion. Let's look at how Rees valuations relate to multiplicities. Okay, so let's assume Rm is local. Dim R is D. The residue field is infinite, just in case we need it. Okay. If I is M primary, of course, we know what the multiplicity is. You can define it in a number of different ways. It's the limit as n goes to infinity, 1 over n to the d, the length of R mod I to the n, which is the limit as n goes to infinity, 1 over n to the d minus 1, the length of I to the n over I to the n plus 1. And then if you think in terms of Hilbert polynomials associated to graded algebras, it's just the multiplicity of the associated graded ring. I don't know, different people write it in different ways. Take the associated graded ring, which is just the sum of these things here. That's the multiplicity.
Then we need to divide by d factorial.
Oh, sorry. Let's see. Right, of course. Let me see. So I put the d factorial up here. Right.
Yeah. Yeah.
If you're taking limits like this. Yeah, sorry about that. Okay, so you can think of it as the multiplicity of this algebra. And of course, there's the famous Rhys multiplicity theorem, which can be recast in terms of Rees valuations. I'll just state the difficult direction. So if Rm is quasi-unmixed, J contained in I M primary, if the multiplicity of J is the multiplicity of I, then V of X is bigger than or equal to V of J for all X in I and V a Rees valuation of J. Now, this by definition is just the min V of Y, such that Y is in J. Okay, something more related to what I'll talk about in terms of work done by Javid and myself is Rhys defined something called a degree function. All right, so we still have a local ring of dimension D, and we still have an M primary ideal. And then you take an X and R such that the dimension of R mod X is D minus 1. Then Rhys defined di of X to be the multiplicity of the image of I in the ring you get by modding out the element X. And then you prove the following theorem. For each M valuation, I guess I should be a little bit careful. I'll use lowercase here. Wasn't quite doing it before. I'll explain that. So these are the valuations associated to the DVRs in capital V, right? So these are the rings. And these are the valuations. So that you get a function instead of a ring. So for each of the valuations associated to an M valuation, there exists a positive integer div greater than 0, such that this degree function is then the sum over V and Vmi div v of X. And this is true for all x's above. So it's not only not in a minimal prime, but you want its dimension to be one less than the dimension of the original ring. Now what happens if you take X sufficiently general? Take X and I sufficiently general. Well, for example, like a superficial element, so that multiplicity of I. Here, by the way, X wasn't assumed to be an I. So that you preserve the multiplicity of I. You can also assume Vi is Vx for all V and Vmi. Then the degree function is just the multiplicity, and you have an equation for the multiplicity. And here in the theorem, which renders the degree function as a linear combination of the valuations, this is a fixed constant independent of x. So you get the statement that the multiplicity is determined by the Rees valuations. All right, well, this looked like a nice formula, so it turns out that Javid and I extended this formula to J multiplicity. Okay, so first, what is J multiplicity? Probably most of you know, but I'll give the definition anyway. Again, we're still assuming Rm is local, dim R is D, and just for convenience, we'll always assume that. Okay, so the J multiplicity it's d minus 1 factorial. Oops, it's the limit as n goes to infinity over n to the d minus 1. So it looks like starts off looking like the same limit. The problem is if you do I to the n over I to the n plus 1, this may not have finite length, obviously, if it's an arbitrary ideal. So what you do is you take the finite length part of it. So gamma m just means everything in the module annihilated by some power of the maximal ideal, which of course is the finite length part of the module I to the n over I to the n plus 1. This is also just the same thing as the multiplicity. You can, just like with regular multiplicity, you can define everything in terms of graded modules. So here R is my extended Rees algebra as before, and this is the normalized. That's where the d minus 1 factorial comes in. Normalized leading coefficient. This is how you know it exists, of the Hilbert polynomial. Associated to gamma m of the associated graded ring. So this is a graded ring. This is a graded submodule of it, which has finite length pieces. So there's a Hilbert polynomial. The dimension of the ring is at most d. I mean, the dimension of the graded ring is d, but the dimension of this part is at most d. So you'll get something, a polynomial of degree d minus 1 or less. And so, first of all, an ideal, these fractions may not even have a finite length part. But an important fact, it's not too hard to prove, Moreover, if this thing has polynomial growth, it may not have degree d minus 1. I should say normalized coefficient of degree d minus 1. And the basic fact is that the J multiplicity is not 0 if and only if the analytic spread of the ideal is maximal. And so sort of the theme in the paper, underlying theme in the paper by Javid and myself is that you can recover and replicate many results involving multiplicity and their connection with Rees valuations that are true for M primary ideals by using ideals of maximal analytic spread and M valuations among the Rees valuations. So here's the theorem, and I'll talk a little bit about it. Same hypotheses as before. Assume the analytic spread is D. In other words, it's a local ring of dimension D. The ideal, let's say, the ideal has positive height. And for each valuation, M valuation associated to the ideal, there's a positive integer, div, such that the J multiplicity is the sum over these V, E, I, V, V, I. So again, the theme is that you can do things for ideals of maximal analytic spread using the M valuations. And when you have an M primary ideal in a nice quasi-unmixed local ring, say, all the Rees valuations are M valuations. So this, but in the non-M primary case, it's important that you only consider these, the M valuations. All right, so the path to the proof is the following, and I'll do a little bit of it. The first is that if R is a local domain, I mean, all of this stuff essentially reduces to the domain case. We didn't state it this way in the theorem, but you take x1 through xd, a minimal reduction, I, and set S to be the local ring you get by localizing T1 at MT1. If you remember, T1 was the birational algebra obtained by joining the fractions x2 over x1 through xd over x1 to the ring R. Because the x's are analytically independent, M extended is a prime, so this is a local ring. And then the J multiplicity of I. Because this is now a one-dimensional local ring, you don't need J multiplicity. It's just the usual multiplicity of I times that one-dimensional local domain in this case. And this is a J multiplicity analog of something I proved in the late 1980s. I think this is a paper I wrote when Jugal was, during the time Jugal was at KU.
Yeah, you wrote the paper in proceedings where you gave a,
Right.
I mean, the the Minkowski inequalities. When they are equalities, that was
That
right.
was a
87.
corollary of the line of thinking that led to this result.
Right.
In the M prime area case, this is multiplicity here. So let's see. Then this next step is to, from this, you can deduce the theorem for R analytically and ramified. And 3, you have to then use the correspondence. To reduce to the complete local domain case, say, which is analytically and ramified. All right, so let me say a few things about this. I'll sketch a proof of the first item because it's not too terribly difficult. And also I'll say a few things about the D's because the D's have information about the completion hidden in them. So okay, so just I'll state some reductions. Doesn't hurt to assume that I is its own minimal reduction. So those are analytically independent elements. And so we'll set script M equal to the ideal in the Rhys algebra generated by the maximal ideal in the local ring in T inverse. Okay. And this is a height 1 prime by the analytic independence because it's the only prime of dimension D containing M and T inverse. Well, it's because it's already a prime. The analytic independence also tells you that when you mod out, it's a polynomial ring in D variables. And the point is, one uses an associativity formula for J multiplicity. And so now I'll just set S equal to R localized at M. So there's an associativity formula for J multiplicity. And it's very similar. You sum over, when you have a graded algebra, you sum over the primes of maximal dimension in the associated graded ring, but they have to contain the maximal ideal. So the multiplicity of I is, the multiplicity of R T inverse R, just by definition. But now you use the associativity formula. There's only one prime that counts because you have to take the minimal primes in the graded ring that contain the maximal ideal. That's part of the requirements of the associativity formula in the context of J multiplicity. So then it's the same, you localize and take length, but that's now just S, T inverse S. And then you do the multiplicity or the J multiplicity of the ring modulo the prime itself. Now I write multiplicity here because these components have finite length already, and this is just a polynomial ring. So this part is just 1. So therefore, the J multiplicity of I is the length of this ring S T inverse S. But that's a one-dimensional local ring. T inverse is a non-zero divisor, so that's the same as the multiplicity of T inverse S. And you can see that you know how the connection between the birational algebras and the Rees algebras, you can see how that's going to work. All right, so, and this turns out to be the multiplicity of IS. So let's just look at that for a second. So Y, E, okay, so what you do is you take the Rees algebra and you invert x1t. And when you do that, you can see that you just get t1 itself adjoin x1t, x1t inverse. Now t is an indeterminate over the ring R. You can just assume we're in a domain, so you don't get too nervous about anything. And so this is actually a variable, independent variable over t1, because this little t is an independent variable over R, or the fraction field of R. And so this is really a Laurent polynomial ring over t1. And moreover, x1t is not in M. So when you localize at M, it's just a further localization of this thing. And the reason x1t is not in M, that's from the analytic independence. These variables are the images in the Rees ring mod M of the xi times t. So what else do we have? So I can extend it, right, to a localization, because it's not contained in the, the thing you're inverting is not in the maximal ideal. Okay. But this turns out just to be M from the local ring itself times R adjoin x1t inverse. And that's just, since T inverse is already in M extended to this ring. T inverse is x1, which is in M, times 1 over x1t, which is in this ring here. And so this is just mt adjoin x1t, x1t inverse. And so now when you localize, if you localized at M, script M here, you get S, but then that in turn is just S x1t. From this equation here, that's localized at M x1t. So you think of this now as a polynomial ring over the local ring, localized at the extension of the maximal ideal. When you extend residue fields, we use round bracket x. So that's just this. It's a local ring, extend to a polynomial ring, and localize at the extension of the maximal ideal. So the multiplicity of IS is certainly the multiplicity of IS x1t. And that's the multiplicity of IS with the script S, which is the multiplicity of T inverse S, which was the multiplicity of the J multiplicity of I. Okay, so that's the first part. Let's see, where are we? Okay. I want to say something. So if R is analytically unramified, let's say it's a domain, and you can assume I is generated, it's a minimal reduction of itself. Here we're still assuming analytic spread is D. Then we have JI is the multiplicity of IS, that one-dimensional local domain. And you have to recall from the first lecture that the VM of I, or the essential valuations, essential valuation rings of S, that's the residual transcendence degree of d minus 1 forces those centers of the DVRs to contract back to M in the ring T1. But now you have S bar is finite over S. That's the integral closure. And so that's by the analytic unramification. And so now you use the formula, the expansion formula, or a different version of an associativity formula for multiplicities, where you extend to a finite extension. So J of I is E of IS. And then you sum over all the maximal ideals in S bar, but those just correspond to the essential valuations, which are the Rees valuations. So that's V M of I. And then the formula says it's what? K MV, not the transcendence degree, the algebraic degree, just the usual degree. And then you do the multiplicity of the ideal in each of the local rings, but in this case, it's just the valuation of the ideals. So in the analytically unramified case, these are the DIV. All right, so in the general case, what happens? I want to say a little bit about what the D's are, because I think it's kind of interesting. In the general case, the Rees valuations, if you remember, the Rees valuations of I correspond to the Rees valuations often the completion, and those are the ones that are actually determining what's going on. So if you remember, each V in little v m of I corresponds to a W in V M R hat I R hat. And each W corresponds to what I call a BW, which is R hat mod ZW, or ZW is a minimal prime in R hat. So the point is, by definition, if you're given a Rees valuation and your ring is in a domain, it really is a Rees valuation of the ring modulo some minimal prime. So each W has a minimal prime associated to it. Of course, different W's could have the same minimal prime associated to it. And so now you set A sub W equal to the length of R hat mod ZW. So you have your Rees valuation over the completion. It comes equipped with a minimal prime, and then it's the thing that you get in the associativity formula. It's the length of R hat localized at ZW. Okay. And now if you set D, all right, so each V corresponds to a W. If you said this equal to AW times D I B W, W. So remember, the DIBW, BW is complete local domain, so it's analytically unramified. So it's just, this term here for the corresponding S. Okay. Then J of I. It's a summation V M I D I B V of I. And because of the one-to-one correspondence, there's one of the, this guy, this makes sense. But it's a little bit unsatisfying. So in the paper, we proved the following proposition. Oops, almost out of time. I'll finish here in just a second. Let's say Rm is a local domain, etc. Residue field is infinite. Analytic spread of I is d x1 through xd. There's a minimal reduction of I, say. S as before. Then if you take V and M of I, this term that appears in the analytically unramified case, this is independent of S. And two, oh, well, I guess I already wrote this. DIV is a WV times K. Oh, I didn't write this, so because I wrote it in terms of over the completion, it's then K. It's the degree of K mv over K ms. So you can express, so here when I wrote this equation, these refer to residual extensions over the complete local domain V sub W. Here I can say it back in terms of V and S, which is all over the quotient field of R. But the interesting thing is you can't get rid of this term. This is the length of the completion localized at the minimal prime that's associated to W, and the W that corresponds to V. So you can't get rid of this term. These numbers have something about the completion hiding in them, even though you can bring this degree extension to the quotient field and residue fields involving R and not involving the completion. This number is still hiding. So an amusing corollary is the following. Suppose Rm is quasi-unmixed, analytically unramified. You can say in terms of M-primary ideals. You could also use ideals with maximal analytic spread. Then R is analytically unramified if and only if, for some, or equivalently every ideal generated by SOP. So you need a system of parameters so you can form the ring S. A multiplicity of I is the sum over V, V M of I. Of course, those are just the Rees valuations. K, M, V, M, S. The point is these numbers are forced to be 1, so that means the length when you localize at any minimal prime is 1, so it's 0, so it's analytically unramified. And you need the quasi-unmixed hypothesis to make sure all the minimal primes are involved. Okay, well, I think my time is up, so I'll stop here.
Okay, thank you, Dan. We can now take questions. And Dan, if you can open your video, is it possible?
No, unfortunately, it's it just won't open. So
Yeah.
sorry about that.
No problems. Any questions from audience? You can open your mic and video and ask questions. So I have, yeah, okay.
No, go ahead. I was just gonna. I wasn't gonna say anything mathematical.
Yeah, no. So first of all, the analog of Rees multiplicity theorem is valid for J multiplicity, I suppose.
Right. Of course. Yeah. I didn't mention that, but that's certainly true.
Right. And
Flanner and Manarese did that.
right. So
I mean, there's lots. Go ahead.
Yeah. So the hypothesis is same. R is quasi-unmixed, and but you have an ideal of analytic spread and J multiplicity of J and I are equal if and only if J is a reduction of exactly same theorem holds.
Yeah, that's Flanner Manarese's theorem.
Okay.
And then Ulrich and Javid, as most people know, Bernd Ulrich was Javid's advisor. And so they did module versions of the Flanner Manarese theorem as well. I mean, this is just, this was all about ideals. I mean, Ulrich and his students have extended, all this J multiplicity stuff to modules. Was originally, some of it was done by Rhys and also Kleiman and Theorem. So, but it, it's definitely, I mean, what I've done is, what I've talked about here is just pretty, just referring to ideals and not nearly as difficult as what other people have done. I did want to say, since I see him there, hello to Peter. I hope you and your family are doing well.
Yeah, Peter is going to speak later in the seminar sometime, and yeah, give 2 lectures. Yeah.
Right. So yes, I hope, Peter, I hope you and your family are well and staying safe during these, unusual times.
Yeah.
Well,
yeah, I had one more question, Dan.
Okay, sure.
Yeah. So you use this technique to prove the Minkowski equalities are true if and only if the ideals have equal integral closure. There is no containment relation among the ideals now.
Right. That was well. Actually, all I did was the crucial case was done by Rhys and Sharp. My paper in the 80s just showed how to reduce to the 2-dimensional case. Right.
So, of course, as you said, Rees multiplicity theorem is valid for J multiplicity also. So, obvious question is, when you are given two ideals of analytic spread equal to the dimension, can we do something similar to Minkowski inequalities and Minkowski inequalities with J multiplicity?
I don't know. I mean, part of the problem is having a good theory of mixed multiplicities. And Javid and I thought about that at one point and had some partial results. If you try, I think we saw at one point, if you try sort of the obvious thing, where if your ideals, let me see, if I go back to my camera. Can you see that?
Yeah.
Okay. You might try something like, what is it like? You might try looking at, the lengths of gamma m of I to the n j m over I to the n j to the m plus 1. Right, this is kind of what you would do. This is one way to generate some mixed multiplicities, right?
Yeah.
The problem was, I think, was that when we did, I don't remember this a long time ago when Javid was postdoc at KU. In the M primary case, right, there's large overlap between the multiplicities you get here and the multiplicities you get here. They're essentially the same whenever that makes sense to ask if they're the same.
Mm-hmm.
I think we discovered that you don't necessarily get the same set of numbers here.
I see. Uh-huh. Uh-huh.
So it's been a long time since I thought about that, but I think that was one of the problems.
Or you don't get the same numbers. Okay.
Don't hold me to that, absolutely, but that's my recollection.
Okay.
But, it's been 11 years, so.
Yeah. So maybe there is no Minkowski inequality, for example. That is a possibility.
It's possible, but I mean, I haven't, I was chair for 5.5 years, so I haven't kept. There's a big gap in my commutative algebra education, so I haven't kept track of what everybody's been doing in terms of these things.
Yeah, because Katkovsky's work has generalized mixed multiplicities to very general situations, even for non-filtrations and. Yeah.
But did he extend? Were they M primary filtrations or even non-M primary?
No, they are all M primary filtrations, right?
Right. But quite general filtrations with almost no conditions whatsoever.
Right.
Yeah. But those can be done for non-M primary also.
But there is
Minkowski inequality. Yeah.
Okay. For non-M primary ideals, there is a way to get Minkowski inequalities.
Yes, it depends on how you're defining the multiplicity for non-M primary ideals. One, I think Montano and C. Drews, they did one way they proved the Minkowski inequality, and there is another way also to you can prove the Minkowski inequality for non-M primary ideals.
Okay, so it doesn't go through the root of J multiplicity.
No.
Okay. All right. So, any other comments or questions for Dan? I guess not. So we can close the seminar today. We all thank Dan for his very interesting talks and can clap. Okay. Yeah.
Okay, great. Well, thank you. Good to see everybody. All right. Hope everybody takes care.
Yeah. Okay. Bye-bye. Bye-bye.